Hello there, 8th graders. This is Mrs. Minowitz, and I'm here today to talk to you about both the Milky Way galaxy and about stars. So one of the things I want you to understand about space is this idea of dark matter and dark energy. So dark matter is a type of matter hypothesized in astronomy to account for a large part of the mass that appears to be missing from the universe. Dark matter cannot be seen directly with telescopes. Evidently, it neither emits nor absorbs light. Instead, the existence and properties of dark matter are inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. So basically, dark matter is this concept that we use to help explain different things. We can't observe this matter, but based on how other things act, we know that this matter has to be there. It is thought that the total mass energy of the known universe contains 4.9% ordinary matter, or what we think of as matter, 26.8% dark matter, and 68.3% what's called dark energy, which is a hypothetical form of energy that permeates all of space and tends to accelerate the expansion of the universe. So very little of what we think that space actually is are we actually able to understand and observe. So now we're going to start talking about the Milky Way galaxy. And the sun is one of billions of stars that are in the Milky Way galaxy. And there are different shapes that galaxies can have. The Milky Way galaxy is what's called a spiral-shaped galaxy. And on this next slide here, it's kind of like an artist's rendition of showing the Milky Way galaxy. We don't actually have a picture of the Milky Way galaxy. And that's because we're in the middle of the Milky Way galaxy, or inside of it. It's kind of like trying to take a picture of the outside of your house when you're inside of it. It's just not possible. Same thing for the Milky Way galaxy. But if you take a look at this diagram, you can see some different things. First of all, if you were to go across the Milky Way galaxy, it's estimated that it would take, or the distance would be 100,000 light years. Okay, so huge distance across, and the sun is about right here on this drawing. And then here's the central bulge, and everything in the outside of the galaxy spins around or revolves around the center of it. So one journey of our solar system around the center of the Milky Way galaxy is called a cosmic year, and that takes approximately 225 to 250 million years on Earth. This is another diagram showing what they expect the Milky Way galaxy looks like from its side. Okay, where you can still see this central bulge in here, but again, this is not an actual picture. All right, as we start to look, we're going to transition here and start to talk a little bit about stars. When we talk about stars, one thing I want to cover is distance and what units we use for distance. So when we're in our own solar system, we will use astronomical units. They make sense. They're just the right size to use to measure things in our solar system. However, when we are talking about galaxies, we're going to use light years. And even though it has the name, or it has the word year in it, light year is not a time. Light year is a distance, and as the distant light travels in 1 year, which is why it's called a light year, and that is equal to about 9.5 trillion kilometers. So it's a very, very large distance. We only use it when we are talking about galaxies, but to put that into perspective, if you look back at our diagram, remember that the Milky Way galaxy is 100,000 light years across. Okay. Now, stars, okay, have what's called a life cycle, just like you or I or other living. of what's called the Crab Nebula, and this is where stars are formed from, is what's called the nebula. On the back of your handout, I have a diagram that shows what happens to different stars after they are a nebula. So it's comparing the low mass and high mass stars. Okay? We'll talk about this in more detail here. Our sun, okay, falls into the low mass stars group. It's medium sized. It doesn't have a lot of mass. It's pretty much an average star. Okay? It's yellow in color. Over time, okay, it is going to change what stage it's in. So the life cycle of a star the size of the sun is about 10 billion years. And the first stage is what's called the main sequence, and that's what you typically think of when you're thinking of stars. This is 90% of all stars. However, at the end of their life cycle, they will become a red giant. They will actually expand in size. Then they will become a planetary nebula, and finally a white dwarf star. So I have a video here I'm going to show. Okay, it's a minute long that shows this process.
From the deep, cold reaches of the solar system, flying in toward the sun, passing the orbits of Neptune and the binary pair Pluto and Charon. We are seeing our home system as it may look about 5 billion years from now. Looking closely, we see that something's gone.
Okay, so here you're starting to see our sun going from a main sequence star to a red giant. And if you look here, it is reaching all the way out to where the Earth is. Okay, so that is the second stage, a red giant.
And puffs off shells of plasma and gas.
That becomes unstable, and then it's going to form into a planetary nebula here. That's what's shown right now.
Nebula for all the galaxy to see. What remains of the sun now shrinks down to become a dense, cold, white dwarf star.
Right? Then over time that shrinks down and we're left with a white dwarf star. So it kind of shows you the different stages of what is happening for a low mass star. And now this life cycle is about 10 billion years. This will happen to the sun, but we're only about halfway through its first spot in the first stage. So in about 5 billion years, we're looking more towards the red giant stage happening. Okay. Red giants are about 10 to 100 times larger than our sun, so that's why it's stretched out there and its heat would go much further than what it does right now. And our sun has a radius of about 700,000 kilometers, so if you imagine 10 to 100 times that, that is pretty large. To put the size of different stars into perspectives, this shows you some of the different stars. This largest one here is 600 light years across. And to put that in perspective, the sun here is 1 pixel on this diagram. Okay, so in terms of stars, our sun is nowhere near big. There are much, much larger stars that we're going to take a look at and talk about in class. But sun is pretty average, not very large. Those large stars fall into this high mass group. Their life cycle is much shorter, only about 10 million years. And they stay on the main sequence. And then after that, they become red supergiants. And then they have what's called a supernova, which is usually fairly short, but it's basically like your star explodes, and then it becomes either a neutron star or a black hole. Neutron star, whether it becomes a neutron star or a black hole depends on how massive it is. If it's high mass but not the largest ones, then it'd become a neutron star. If it's one of the largest ones, then it would become a black hole. Now, a neutron star, okay, is basically called a neutron star because it is very, very dense, and its protons and neutrons, or protons and electrons, excuse me, are forced together and form neutrons. That's how it gets its name. Due to the density of a neutron star, 1 teaspoon of it would weigh 1 billion tons on Earth. And according to astronomer and author Frank Hsu, a sugar cube of neutron star stuff on Earth would weigh as much as all of humanity. So it is very, very dense. Now, black holes we'll talk about more in class, but that's also a final stage for things that have a very high mass. And it is thought that there is a supermassive black hole at the center of the Milky Way galaxy. It is called Sagittarius A, and it has a mass equal to about 4 million suns. So it is very, very massive, but its volume is not as large because it could hold, the volume could hold a few million Earths. And if you compare the size of the sun to the Earth, that means it is very, very dense. Okay. We'll talk more about stars and black holes in class.